So the two videos this week will do a brief introduction to one of the more difficult concepts in this course, the pumping theorem. So before you start, you should be reasonably comfortable with the regular languages and deterministic finite state machines. So just a quick review to get things in your head. You all remember what symbols are. You remember that strings are concatenations of symbols from an alphabet, which we usually represent with sigma. You know that a language is a set of such strings, again from an alphabet, and the language may be finite or infinite. You know that the regular languages are a special set of languages, and they are the ones that can be decided by deterministic finite state machines. And you remember that non-deterministic finite state machines add no power. They can still only decide the same set of languages as the deterministic cousins, which is the regular languages. And you should be aware that there are some languages that are not regular. So, the finite languages. We know that all languages which have a finite number of strings are trivially regular. That is, we can easily build a non-deterministic finite state machine and therefore a deterministic finite state machine for any of these languages. And the way we do that is we build a simple set of states that just accepts in a chain the one of the strings in the alphabet. Then we build another one for the next string in the alphabet. And so on, for every of the finite number of strings in the alphabet. Now, because each string is finite, and because we're discussing a language which has a finite number of strings, this will result in an overall finite number of states. Then we build one start state and connect it to each of these little submachines with an epsilon transition. So we can see very quickly that this machine will accept any finite language that we decide, and because we can build from any non-deterministic finite state machine an equivalent deterministic finite state machine, we know that every finite language is therefore regular. Things get a little bit trickier when the languages get infinite. Now, when a language is infinite, that means that there is not a finite number of strings. But what it does not mean is that any individual string is infinite. Every string in the language has a finite number of symbols in it, but we don't have an upper bound for the number of symbols. So we can always build up a new language. So something like A* is an easy example for an infinite language. None of the strings that we build using A* have an unlimited number of A's, but we can always build a bigger string, so we never have an upper bound on the size of the strings. So, what do we therefore know about the maximum length of any string in an infinite language? The answer is nothing. Because the language is infinite, it's unbounded, and we can always get a longer string. We also know that we can find, if the language is regular, a deterministic finite state machine, which must have a finite number of states, and we have an algorithm, min DFSM, that, given any other DFSM, will build us the smallest possible one, and therefore we know that we have a smallest possible machine with a finite number of states for any regular language, even though some of those languages may have strings which are unbounded in length. Now that's an important thing for later. So let's look at these two machines here for a second. If you look at the top machine, it contains no cycles. Now what is the maximum length of string that the machine on the top can accept? The answer is simple. It only accepts one string, 101, of length 3. But you can see that if I ever have a machine without any cycles, it will move from one state to the next, and if it has n states, it will always only be able to accept at most a string of length n minus 1. Now let's look at the bottom finite state machine. What is the maximum length of string that this machine can accept? You should have pretty easily come up with the answer that there is no upper bound on the length of string that this machine can accept. And it's pretty obvious that this machine will accept an infinite regular language. So this machine will accept 101, just like it's the machine above it. What lexicographically, and I want you to pause the video and think about it, is the next string that that machine will accept? The answer is 1001. Lexicographically, what's the next string? 10001. We can see that each of the strings that gets built up from the previous string gets built up by shoving a little zero in the middle. It's sort of like we're expanding from the middle with zeros. So, a general statement that is true is that if we have a machine with n states, that machine can accept strings of a maximum length of n-1 without looping. The reason is, if we start in one state, we haven't accepted a string of any length. When we move to a new state, we always consume one character. That's as per our definition for a finite state machine. So, each time that we move, we have one less possible state to move in without going back to a state that we've already visited. And by the pigeonhole principle, the maximum length of a string that we can accept will be n-1 before we have to go back and visit a state that we've already seen. Okay, so if we have an infinite language L, which is regular, then there is a minimum DFSM which accepts it and can be represented by the tuple form that I've put down here. Now, this machine has k in bar states. By the pigeonhole principle, as we said before, when the machine accepts a long string where the length of the string is greater than or equal to the number of states, then it must visit at least one of the states more than once. That's important. Therefore, any such string, which, as I said before, has a length greater than or equal to the number of states in the machine, must go through a loop in the DFSM. If it has to go back to a state it's already visited, then there is a loop and that string is going through that loop. But because there's a loop, that means that there must be a way to go through the same DFSM without going through that particular loop, or a path where we go through that loop a repetitive number of times. So, looking at the machine below, if we have a length, this machine has 4 states. It can accept a string of length 3 without revisiting any of its states, and that string is 101. But as soon as it accepts a string of length 4 or more, it must have gone through a loop, and this is the loop we're talking about. Now, if we have gone through that loop and revisited state Q2, then we must have been able to have just continued on without going through that loop, just by stopping in Q2 and moving on. And we know that's true because 101 is accepted. Or if we have, say, accepted 1001 and have gone through the loop, then we must also be able to go through that same loop as many times as we want. So, by that principle, we can keep shoving zeros into the middle of our string here. So, we call this process of removing a bit of a string that has gone through a loop, or repeatedly inserting a bit of a string that has gone through a loop, pumping the string. So, when I have 1001 being accepted by the machine, and I say, well, this part here went through a loop, so I can remove it, we call that pumping out. Or, if we instead say that because that section went through a loop, I must be able to insert it again afterwards, we call that pumping in the string. And we can pump in as many times as we want, and we can pump out at least once. So this is a lot to digest at this point, But by the end of this particular video, what you should have grasped is that when we have a long string, and that string is accepted by a machine, then that requires that the string went through a loop. So whenever we accept a string of length greater than or equal to the number of states in the machine, then that string must have gone through a loop. And you should know what I mean by pumping said long strings. So when we have such a long string and we have a piece of it that went through a loop, we can remove it from the string, or we can reinsert it in that same place in the string over and over and over, because we can go through that loop 0, 1, 2, 3 as many times as we want.